Uh, After this good presentation, we have the three use cases that three of the companies will be sharing. I would like to invite Prasad Panchangam, founder CEO of CloudXM. Can we have his presentation up?
Hello, thank you. Thank you. Hello, everyone. Can you hear me? Okay. My name is Prasad Panchangam. I have a consulting business called CloudSim Technologies, but I have now been, for the last few months, involved with starting a company in the AI edge processing space, particularly silicon. So I'm a silicon guy, and I'm going to sort of give you a silicon flavor for AI edge processing. And I was originally scheduled to be on a panel at 2 o'clock, but then we kind of swapped, and I'm doing this presentation. This is my agenda. It's an incredibly ugly slide, but essentially what I'm trying to say here is I'm just going to quickly go through the background and context of what I'm going to say, because that's really important. You need to understand, what algorithms I'm talking about, what specific aspect of the ecosystem I'm talking about, and so on. And then there's current products. I'd like to quickly cover that. Most people look at the edge in different ways, look at AI in different ways. So I'd like to set that stage. And then I want to cover the challenges that we in New Netra are trying to address. And then like to give you, a little bit of a view into what the core offering is and what we're trying to do. So my background is primarily in chips and systems. I was a senior director of technology at AMCC, doing all of the ARM64 stuff for the data center, SoC. That's now been called Ampere. It got acquired by Ampere. I was in Microsoft for several years, doing a lot of the media SoCs that, we actually pioneered a lot of the IPTV set-tops and so on. So I'm very familiar with, general purpose CPUs, DSPs, fixed state machine accelerators, and so on. So when I go through this presentation, I'll sort of touch upon all of these things. So first thing is this big slide. Everybody knows this, right? So if you look at a lot of AI today, almost literally 90% of it is done in the cloud. So you have offerings from Google, you have offerings from Microsoft, you have offerings from Facebook, you have a lot of these guys who run a lot of classification, object classification, face recognition, and so on in the cloud. There's also a lot of devices, embedded devices that you see in the home today that essentially connect to the cloud and do a lot of recognition there. So you'll see, if you go to one of these Chinese shows where they sell all these devices, every one of these devices will have some cloud connectivity to connect up to the cloud and be able to recognize objects and so on. But there is a definite push to move all this intelligence, not all of it, but at least the inferencing part of it from the cloud into devices at the edge. And obviously, these are at the bottom, you'll see what the benefits of this are. First is obviously latency, right? If you want to send something to the Google Cloud, the round trip time might be 300 milliseconds. It might take you several seconds for you to recognize an object, which is probably a non-starter for the use case. There's also low power because you need a lot of power to power up the radio, push data up to the network, and a per inference power footprint is going to be high because you're going to do all this in the data center, which is all running on high power hardware, has a lot of HVAC and so on. So power per inference is very high. So low cost, obviously, again, every time you access the Google service, you have to pay for it. It's not free. So Google essentially amortizes their CPU cost to you. And then privacy, obviously, because every time you take somebody's picture and push it up into the cloud, it's a privacy concern. So because of all of these reasons, there's a definite push to the edge. Now, before we launch off into what it is that edge is all about, AI means different things to different people. I just took this picture from a McKinsey report. They have a whole spectrum of techniques, from traditional techniques to advanced techniques. And you'll see that AI is essentially a vast space. Everybody is confused about it. Everybody thinks AI means feed-forward neural networks. That's not true at all. I mean, AI, or data science, as some people like to call it, I mean, a naive base classifier is also AI. So in this presentation, I'm not going to be talking about any of these things at the bottom. Modern vision use cases like recognizing somebody's face, recognizing an object, figuring out somebody's speech pattern, figuring out what text can be represented for a particular spoken word, and so on, don't use any of these techniques. Most of them use what are called convolutional neural networks, and a lot of new techniques called recurrent neural networks are coming up, particularly for speech, because you need to have some memory of what was said before you can classify something that is being said. So there's a lot of recurrent and convolutional neural networks that is forming the bulk. So, our colleague from ST just talked about, all of these networks. They're all convolutional neural networks. So doing things like pooling, adding sigmoids. So whenever you look at a TensorFlow script, when you see adding convolutional layers and max pooling layers and sigmoids, they all refer to convolutional neural networks. So for the purposes of this presentation, that's all I'm going to talk about. Transfer learning and reinforcement learning, not as much, because they cover a lot of training aspects, and I'm not going to be discussing training. That's the other thing I'm going to say. At the edge, people usually do inference. So you've got to understand the difference between inference and training. Inference is you have a trained model, you look at a real-world signal coming in, and you predict or classify what that is based on the model you already have. Training is creating that model, which is a much more CPU-intensive effort, and it's looped multiple times, and so most of that is done by big NVIDIA GPUs in the cloud. So general-purpose GPUs do a lot of the training in the cloud, but what we're going to talk about is inference. So here, the definitions for this presentation, AI in my dictionary for the purposes of this presentation is deep learning techniques using ANNs, and they can be used to solve a variety of problems. And in terms of the techniques, I am not going to talk about SVMs and linear regression and all that. I'm just going to talk about classification and continuous estimation. Again, this is most widely applicable for the edge, because today's edge, as you'll see later on, is mostly about vision, camera use cases, speech, text, healthcare, where you figure out something from the signal and so on. So, I mean, we are talking about a very narrow set of AI techniques and AI algorithms, but for the purposes of edge and IoT, this is what we should focus on. And again, the focus again is on feed-forward neural networks and recurrent neural networks and CNNs. And what McKinsey says is just these three techniques enable somewhere between 3.5 to 6 trillion worth of value. So that just gives you an idea of how much of money is behind AI and particularly these techniques. So again, so I just wanted to put this up here just to give you an idea. Just look at the top two. Problem types of classification and continuous estimation. So everything from security cameras and drones and wearables and medical devices, smart speakers, head-mounted displays. Think of anything you want, they all fall into the first two things. So that's where the maximum value is, and that's where all the money is going to make silicon and so on. All right, so let's look at the edge. What do we have at the edge? Current products, right? So edge IoT means what? So I want to cover smartphones first, because this is where the bulk of the volume is. This is where the bulk of the investment is. And if you look at this space, you'll be blown away, because every one of the big guys has invested literally hundreds of millions of dollars to put what they call neural engines into their smartphones. So if you have one of these Apple phones, 7 plus and above, you probably have an A11 or A12 chip. They call it the Bionic chip. It's a really nice marketing term for something that has an integrated inference engine. So all of these are inference engines. You don't train networks on a smartphone. You inference from a real-world picture, trying to classify what this picture is. So the Galaxy S9 has, a neural engine from DeFi. DeFi essentially is now owned by Xilinx. They sold themselves to Xilinx, and it's part of the Xilinx suite, ML suite. So the Chinese guys have, the Huawei, and there's MediaTek. MediaTek has an engine from Cadence. Cadence acquired Tensilica. Tensilica has a neural network processor. So if you look at all of these guys, they have pretty large, neural network accelerators on their SoCs. And when I say pretty large, these are large in terms of area, in terms of energy, in terms of bandwidth. I mean, the system data bandwidth that something like a Cadence P6 requires is something like LPDDR4 bandwidth, something like 10 gigabytes to 20 gigabytes per second. So these are all big engines that run on all of these things. But you'll see that there is, a big trickle down of these engines to mid-tier phones. So you don't have to buy the most expensive phone to get these things. They're all coming down into cheaper and cheaper phones. So this should give you an idea that, a smartphone is really at the edge of the network. There's a lot of, investment in, AI that's going into these. Now, why would you even need an accelerator for some of these things? I mean, some people may have, may think that why can't they just run all this on the CPU? I mean, CPUs, general purpose CPUs, unfortunately, don't have this kind of efficiency as a fixed state machine accelerator to do neural network applications, to run the mathematical operations. If you look at a convolutional neural network, every convolutional layer is a multiply accumulate. And a fixed state machine accelerator simply has 10x, maybe 20x more efficiency than a GP CPU to be running all of this stuff. So there is a huge market for people building accelerators to go into these things. So this is sort of the table stakes for smartphones. So what about IoT? I mean, this conference is all about IoT. So what has happened is that today, essentially, you see three things that are driving a lot of AI. There's voice assistants, which is all your Alexa and Siri and OK Google and all of these, Cortana and all of these guys who need to be able to recognize your voice and figure out what is it that you're saying and be able to execute an action. So voice assistants have driven a lot of IoT. And again, today, if you buy a smart speaker, it's most likely going to be connected to the cloud, right? Siri on my iPhone doesn't work if I'm not connected to the cloud. But there's a huge push to move a lot of this onto the edge so that it doesn't have to connect to the cloud. So this is going to translate into the bottom panel here, which is, as this intelligence moves into the edge, then, things like industrial IoT and consumer IoT, like wearables and video doorbells and smart homes. Video doorbells is a huge use case in the US. I don't know if you know this, it's kind of funny, but Amazon really loses a lot of money in people stealing stuff from other people's homes. So an Amazon guy comes, brings a package, drops it on your porch, goes off, you're not at home, somebody else comes, picks up the package, it's gone, right? So Amazon essentially loses a lot of money there. So they're investing in a camera, a smart camera, that's on the door, and if the Amazon delivery guy shows up, the camera looks at that guy and says, oh, this is the Amazon delivery guy, and opens the door. And the guy drops, or he opens a small side door, like, the door that the dog goes through, so that he can just drop the package in through that. So it's a big deal. Video doorbells are big deals. So this is where we are getting to. And there's a huge push now. There's a huge amount of investment in consumer IoT and wearables, right? I mean, every one of you who has one of these things, it's getting smarter and smarter, right? I mean, you have a Series 3 or a Series 4 watch, you walk 20 steps, all of a sudden it knows you're walking. It says, hey, shall I turn on the workout app? So today you have a Series 4 watch, it looks at your ECG and says, you're probably having some sort of atrial fibrillation or something like that. So these things are getting smarter and smarter. And going forward, there is going to be a lot of push in this space. I want to talk about smart cameras, right? So I don't know whether you guys know this. In China, there are literally 300 million smart cameras. They look at everything. They look at kids in the school. They look at whether the kid is happy or not. They look at your car. They look at where you're going. You show up in China. You go through immigration. And then there are like millions of cameras tracking you. Where are you going? What are you doing? It's crazy. It's unnerving. But they have it, right? This is a picture. You can actually see a whole bunch of cameras looking at a scene of people. They're classifying every person's face in that scene. They're looking at every vehicle that's on the road. And they're actually going to go to 400 million cameras now. I mean, it's like a gigantic spider-like, country with like octo eyes everywhere. So there's a huge market for surveillance, obviously, and cameras and vision and figuring out what is in the scene is a huge deal in AI. And this is what is driving a lot of edge IoT smartness, if you will. So there's a lot of Chinese chip makers, right? There's Cambricon, there's HiSilicon, Horizon Robotics, Kendrite, all of these guys who are building, and there's almost a dozen more startups in the Beijing and Shanghai regions that are building all of this stuff. And Intel is, I just put Intel up here, but FlexLogix has a part, and NVIDIA has a part. Every one of these guys have a part. And there's companies like Simple Machines and Wave Computing. All of these guys are building parts. But what I want to point out here is that custom hardware enables much more complex deep neural networks than a CPU can handle. So smart cameras is probably going to be the biggest driver of fixed state machine accelerators than anything else, because vision, the vision use case is probably the biggest. And our colleague from ST talked about the drip bottle. That's a vision use case. You look at the bottle, figure out how much there is in, how much fluid there is in it. So this is one thing I wanted to talk about. Now this is where we get down to the bottom end, right? IoT sensors. Now, what is it that we can do in IoT sensors? A person walks around with a Holter monitor, right? You have a little device that you put on your chest. It runs for a week, and then it collects data. You take it back into the hospital. They hook it up. It sucks out all the data from the flash in there, and then a report is generated by how much of arrhythmia they see in 48 hours, 96 hours, 1 week, whatever. But the real clinical demand in that market is don't come back after 1 week. If you're having an episode while you're wearing it, we want the device to know, and we want the device to flag it. So there's a lot of intelligence that needs to get on sensors, on body, and into the sensor. So you have these really tiny microcontrollers, and if you can't have like a Cortex A9 or a 64-bit ARM core or like an x86 big core be very inefficient at processing deep neural networks, what can you do on a Cortex M series or a Cortex A series processor, right? So ARM has its own strategy. They're coming up with something called Helium, which is their instruction set extension for AI edge processing. But they have a Cortex M system, software interface spec. They have neural network extensions to it, and you can port your DNNs to it. But then there's other companies, right? There's Sentient, which is trying to build an analog, what they call a neural processor. Then there's Greenwaves, there's Eta Compute, and there's a lot of these guys that are trying to build processing capability for these sorts of devices. So quickly, what's the challenge that we are trying to address? So I just kind of gave you a landscape. There's smartphones at one end of the spectrum, there's cameras, and there's edge IoT devices. But if you look at a system designer, what is it that they really want, right? A vendor needs a path from a data spec to a product, right? If you go to a systems guy who says, I have data for my use case, now I want to build a product for it, right? So you can't just say, okay, here's a little chip, go build your thing on it. They just don't have the smarts for it. Nobody has big, deep, data science teams to do all of this stuff. The second thing is, you need to have the flexibility to choose between different platforms. Do I want to run this on an existing ASIC? Do I want to run this on the CPU, on a Cortex M series processor, or the STM32 part that our colleague just talked about. Do I want to run this on a lattice, tiny lattice FPGA that goes into my device? I think you guys know this. All the iPhones have a lattice chip in it, right? They all. So whenever you say Siri, it says it's the lattice part that actually wakes up. It's asleep. It wakes up on that little Siri thing, and then it wakes up the rest of the phone. So there is a part in there. So so you need to have the flexibility. And chip designers need a tool to generate a processing engine from a model, from different model parameters. So if I have a model, how do I know what capability, what sort of capability, processing capability I need? And then you need area and performance optimized IP. So this is where we sort of come in. So what we are saying we are going to do is we're going to create a tool which we call the New Netra Design Studio that will essentially take a model and a weights file essentially that's provided by the customer and turn it into IP, soft IP that you can put into an ASIC. So we can do FPGAs, we can do microcode that goes onto a MyriadX if you want, or on a Jetson Nano, or we can do synthesizable RTL that goes into. Sorry, I'm completely out of time, but if you have any questions, I'll be happy to answer it. That's all I had anyway. This is the value prop that we're saying we're going to bring to the table. But if you have any questions, I'd be happy to answer it.
Thanks, Prasad. Thanks, Prasad. Please give him a big hand. We'll just wait for a minute. Can I have Arul Arya, IASI, to come and hand over the memento, please? Excellent. Excellent. Thank you. Can I have Bipin? Bipin Pradeep is co-founder of GIA Smart Cities. He's going to be talking about for the next 20 minutes on the second use case. Please welcome Bipin. Can I have Bipin's presentation, please? Yeah, click it.
Thank you. Thank you, Gaurav. Namaste. Good afternoon. I have 20 minutes. I'm going to go straight to the point. But before me, Danilo and Prasad give an excellent, give you all a whole lot about tech. So I'm not going to talk about tech at all. This is going to be my agenda. We're going to slightly talk about what we at Gaia do. Danilo has already spoken about a bunch of things that we did together, so it'll be even shorter. I'm going to talk about what we offer, solution as a service, and then how we're trying to do scale. You'll understand that as you see my presentation and I talk about why we need to achieve scale. And then finally, something about how we overcome some of these challenges, which I call disorder. So in a really one slide, in the quick gist, this is what we do. As of today, we monitor over 86% of India's cheese. And I say effectiveness because it's not about quality, it's also about managing the whole cost-benefit analysis. We monitor and make sure about 71% of India's butter is good for consumption, its whole effectiveness. And we also do almost 40% of India's airports, managing passenger efficiencies. And that number says 10% of India's railways, but it's actually more. We monitor about 1,500 trains as of today. In the gist, this is what we do. We monitor campuses, warehouses, railways, metro stations, airports, hospitals, food and retail, city public, and railway coaches. So while there's a whole lot of tech, which the others have given you, what I'm trying to do is just try to run a business, and struggling at that actually. So this is what we do. We give real-time visibility to the operations. We provide action engines. We optimize experiences and operations. We make whatever was previously digitally opaque, we make them extremely visible. And finally, we do a lot of governance monitoring. This is the span that this is the spectrum of operations, our spectrum of operations. This is, how we impact your lives, the customers that we do. In numbers, that was percentage what you saw earlier. I think we touch at least 7 million users every day. So far, we have gathered 70 million unique user data points, users as in you and I. We have got over 150 million sensor data points. We monitor over 90 million square feet of built area. That means spaces like this. And we started off with cities. So we monitor over 450 million square feet of city areas. So that's the numbers that, that we do. And the reason I'm telling you all this is because of how we manage this. So in the gist, this is all that we do. We look at a site, airports, planes, trains, it can be anything. We gather data from that, you say it's insight, and then we predict, which is what we call foresight, and we either improve processes or do workflow automation. That's it, that's what we do. It's a whole lot of IoT, but as you must have seen, I haven't spoken about IoT at all. We just do foresight, process improvement, and workflow automation. This is the business we're trying to run. These are the different form factors of the devices. Danilo's not here. Oh, there he is. He'll be happy to see that, what we do with ST and a bunch of others cover these different form factors, right from a unit that gets sensor data to what you must have seen in airports, that also has sensors, by the way, to what you must have seen in Swachh Bharat. We do this for about 128 cities. We monitor their Swachh Sarvekshan, as they say, and different other form factors. This small piece is what does all of that. It has Wi-Fi, it has BLE, it has 2G, 4G, it has a facility for having multiple sensor interfaces over I2C, ADC, USART, GPIOs, I2C, different manners in which you can connect sensors. This is what it is. And it has over, allow me to brag, over 12 or 13 different ST components. So this is the piece. There are others too that how we connect sensors. You can connect over 20 different sensors. And I'm telling you this only because you will see how we connect sensors and what data we get out of that. This is it. This is what we connect different sensors through. It's as small as this. And I'll probably show you something even smaller a little later. Those are the interfaces. So what I have connected there and what you see is something that probes in vesicoolers. We monitor the temperature in vesicoolers, or maybe even for Amul in the chillers. Sensor data can come through Bluetooth. So you can have several of these units sitting around, as small as that, and the data comes through BLE or BLE mesh back into this unit that you see. So this is all live, as you must have understood by now. And what we do with all of this, and as I said, we just do two things: process improvement, workflow automation. If at all I talk about workflow automation and process improvement, the first example I can give you is an industry here in Bengaluru. We monitor the number of presses the machine makes. So the customers are not interested in the number of presses. The customer is interested in knowing how productive that machine has been. So you count the number of presses, it has been 80% productive through the day or 90% productive through the day. And as you can imagine, you can draw analytics, and then we find out that the machine is most productive on Fridays and Saturdays, not Mondays. It's the least productive on Mondays. So, customers aren't interested in how we do it. He just wants to know how productive his machine has been. We do this for Amul, where we monitor the Amul warehouses, where we monitor temperature, number of times the doors were open and closed. We ensure quality. It's ultimately about ensuring quality. We do this for toilets, really. You don't have to see whether the toilet is cleaned by somebody pressing. You can put a sulfur sensor in the, as a BLE or an ammonia sensor, and the odor that it generates will tell you whether the toilet is clean or not. And lastly, we do this for BSES Rajdhani in Delhi, where we monitor the power for high-value customers. And what we're trying to do is ensure efficiency. Multiple use cases using the same set, and it's not about IoT, it's about workflow automation, about process improvement. What we do over, foresight, you can predict by gathering some of this data, you're able to easily predict over a period of time. Moving quickly, what I want to talk about is this. It is about how we manage these number of devices, how we manage these number of data points, because as you know, the minute something increases, the second law of thermodynamics kicks in. What is the second law of thermodynamics? It's a disorder. Somebody wants, I'm sure you're all science folks. Anybody want to tell me what the second law of thermodynamics says? It says the entropy of an isolated system never decreases, never. It may remain constant, but that constancy remains only if the processes are reversible. And as we know, no process is reversible. It also says that every system spontaneously evolves towards entropy or thermodynamic equilibrium, and that is a state of maximum entropy. Whatever we do, that's what you realize. We encounter disorder. It is what you call unfailingly there. How we manage disorder sorry, before that, there are some relationships that I've managed to gather over a period of time, and that is, SaaS is solution as a service. If you're trying to do IoT solution as a service, it always increases, or rather it's directly proportional to the number of devices that you have. The more number of devices, you're hitting entropy faster. The entropy of an IoT system always increases with a number of locations. I think we do over 200 odd locations, cities in India. It's a pain to manage them. It's a challenge to manage them, but we do. And of course, I thought of one way in which you could decrease entropy, and that is if you have good security and control features. I think there was a panel discussion on security earlier, and we have seen if you have good security and control features, it does decrease entropy. But of course, there is a thought experiment which Maxwell himself proposed. It says, how do you violate entropy? It's a thought experiment, of course. As much as I said, everything is marching towards disorder. There is a thought experiment that he designed that says, you may violate entropy. And his thought experiment is very simple. There is a demon there sitting across two chambers. It's a thermodynamic thing. So, as the hot particles move, the hot particles are faster, obviously. So he'll open the door, the demon will open the door, and the hot particles go to the other side. So eventually you'll have two chambers with one with hot and one with cold. But remember, this is just a thought experiment. Practically, it has been proven, or so far it has not been proven otherwise. You cannot violate entropy. So how do we violate entropy or try to violate entropy in all these installations that we have? An IoT perspective. So we have two parts. One is what we try to do to escape entropy on the device side. And we say FOTA, COTA, you know what that is, firmware over the air upgrade, configuration over the air. And the other is applied information theory. And the last is what you saw, device versatility. I'll talk a little bit about that. There are other things too. How we manage operations. We have a fabulous operations team. We use extremely good middleware and a good platform, thanks to Azure. I hope the Microsoft folks hear me talking about that. And then, of course, there is the supply chain that we do to make sure, right from the devices, sourcing of devices, to making sure devices reach, all of that is done extremely well. To talk about FOTA, you know what FOTA is, but we have a multiple hierarchy. As you saw, I have devices that talk over BLE as well. And you need to manage the FOTA or the firmware on the BLE device as well as on the gateway or this. So how we manage that is actually taken us over 1.5 years to perfect, to manage FOTA on a device. I see my time going, so I'm going slightly faster. So we try to reduce entropy by building this, by actually having built this extremely good FOTA capabilities over the last 1+ odd years. We're more or less perfected. Just think about it. If I have to even upgrade something here in Bengaluru in Dodbalapur, the cost of service will wipe out my profit for the entire year. It doesn't work, because I have to do things remotely. So yes, I try to reduce entropy by increasing remote management capabilities. Quota, configuration over the air. There's so many things that we can configure. Your connection details, your server details, you may need to change servers, you may need to change server hosting providers, you may need to change Azure properties, your config intervals of data sending. How is it that maybe you don't need all the time? Your Wi-Fi details, sometimes devices are connected over Wi-Fi, that has Wi-Fi too. In airports, Wi-Fi changes all the time. And imagine if somebody had to go to an airport. I mean, forget about going to the airport. The process to get into one and try to change it is complicated. Indicator notification details, you want alerts, you want notifications. How is that you want to change? We allow you to do that. And the FOTA details itself may come from a different server. So yes, so how we configure and then how we control. You need to control the device, your activation, deactivation. So several things that are involved with control and configuration are also done to reduce entropy. You all heard about information theory, Claude Shannon's information theory, but that plays an important role in how we use it. Prasad spoke about intelligence at the edge, but I mean, simple intelligence to apply, it's all that we learn from information theory, which says that the most unexpected events have maximum information. I think you all should be easily familiar with that. If something doesn't occur, I mean, everyday events don't really give you that kind of information. It's something that doesn't, an anomaly is what is important. So the value of information is inversely proportional to the probability of occurrence. That's something that information theory taught us too. So if it doesn't occur that often, don't send it back. Why are you sending humongous amount of data back to the cloud? Process it at the edge, process it at where you are, and then take a decision and then move forward. And then, of course, information that you send over multiple pieces can probably be condensed into one. Yeah, so the total information of two or more independent of many is just the sum of individual information. So figure out what is the right data that you need to send. Instead of clogging the network, clogging your servers, figure it out. Figure out what is. That's what we have figured out. So we've increased the edge intelligence to make value of all of this and then send data. So yes, we have applied information theory hugely. Device versatility, you saw this. We have humongous number of communication interfaces. We have a humongous number of interfaces too, through which you can connect different sensors. But this increases, how all we can reuse the device, where all you can reuse the device. And therefore, everything else, when you have something uniform, everything else becomes lesser to manage. And of course, again, like I said, I hope the Azure folks are listening. We use Azure as a middleware platform. We use a lot of the virtual machine scale sets. Pretty much handed over a lot of things to the middleware so that the intelligence that we do at the edge can pretty much be what we manage. But of course, we have applied it in a way that is useful, in a way that is meaningful, and something that helps us scale across geographies. If I have to deploy something in Spain, I take the sovereign data space and deploy it easily, deploy it quick, without having GDPR issues, etc., facing there locally. And that is something that I must attribute to what has happened in the cloud space, even though we are on the edge. This is my last slide, and I say, even though I've spoken all about entropy and all the negative things, I say entropy is extremely essential. We can't do things without entropy. At the background, if you all can see it, it's a famous painting by Escher. Escher's a Dutch mathematical painter. See, it's a very interesting painting. As you see from the ground, it's land that morphs into birds. And if you look from the left to right, you'll see white birds and black birds, actually blue, but this is major that. You can never see the white birds and the black birds at the same time. It's almost impossible. And that's pretty much one of the things that I want to tell you. You cannot do multiple things in a way without focusing on one. Focus on one, try to get it right, And that is when you will try to reduce, that is when you will decrease entropy. So yes, the only way you can manage entropy with devices, processes, your middleware, your platform, your supply chain, your operations, all of that is we if you focus, only if you evolve in a steady, deterministic manner. You have to evolve. You have to evolve. There's no shortcut. That's something that I've learned. And the thing that we have learned out of entropy is that either you optimize your existing business, existing processes, existing devices, all of that, your middleware, your supply, you learn to optimize it, or you destroy it. You destroy it and you build it. You build anew. And that's what we've been trying to do. Thank you.
Thanks, Bipin. I would request Ravi Gurraj to please come to the podium and hand over the memento. Give Bipin a big hand. It's been great. They've made my job easier. I don't need to police. Thank you. Excellent. So the final use case. Thanks. Can I have Avra Banerjee, co-founder, switch on? So, Avra, you have a problem.
Sorry?
Between lunch
Yeah,
and
I'm
you,
the only one stopping.
yeah, you're the guy. So let's make sure that, we catch hold of all their attention. Thank you. Go ahead.
Right. So try to do it quick so that you guys can go for lunch, but also have some time for Q&A. Sure, I can. Okay. So what we do at SwitchOn is we create digital twins for manufacturing intelligence, and my previous speakers have really set the context with how Edge AI is really important, for industrial IoT, for IoT in general. What I'm going to do is dive in specifically with respect to industrial IoT and try to give you more contextual information about Edge AI in industries, right? This is the basic outline about what I'm going to speak about. I think I can skip this for now. Right? Yeah, so I started off developing Formula race cars in college, moved on to Schneider Electric, where I worked on wireless sensor networks and signal processing. And I spent some time developing power systems for lunar rovers and landers. So I come from mostly electrical product development. That's what I've been doing. And in 2017, we kind of quit to start SwitchOn. And this has been our journey. 2019 is not on there. I've forgotten to update. But we released our digital twin platform back in 2017. Right now, we have deployed it across manufacturing in automotive and FMCG. Those two other kind of sectors we focus on. Right. Yep. So now getting into industrial IoT, and a lot of you might have come across Industry 4.0 and are well aware of that. What's the interesting point about Industry 4.0 is a lot of it was not defined when it started, right? Everyone knew that machines are going to create tons of data, and we have to somehow utilize that to give insights, right? That was the premise, but no one really realized how much data, what kind of processing is required. So the simplest thing to do was, connect these sensors on machines and start streaming data to cloud servers, because that's the easiest thing. That's what you think, when you think IoT. Let's put a Wi-Fi or let's put a gateway there and let's start streaming data. Soon, like we as a company, we also did that, to be honest. We started streaming data to the cloud and started giving analytics. And after a few months of deployment, we just realized the amount of data we are streaming from machines in a day is equal to amount of bandwidth they're consuming in a month, right? And I'll come to that in detail in a few more slides. And that's where we as a company feel that there's a shift from internet-only applications, industrial IoT, to more edge AI, edge IoT, whatever you call it, these kind of applications, right? And that's where Industry 4.0 is kind of headed. So again, a lot of this have been covered in previous slides. Why edge? So these are, 4 points that I have from our experience of over the last 2 years trying to sell to Indian manufacturing especially. Number one is you have to realize machines are real time. They can't wait for your servers to restart. They can't wait for a bug or some of your application sets not working or any of that. These are hardcore real-time system. If you look at a robotic arm, they have precisions up to microseconds, right? And if your application is trying to do something with that data and it's going to depend on your servers being offline for a minute, it's just not going to work, right? The second point is network uptime. Any IT team and any manufacturing facility who says 100% network uptime is a complete myth. We have deployed across 10 factories, more than 10 across India, and we have never hit uptime percentages more than 80%. Max we have gone is 85. Because you got to realize in any network architecture, there are multiple things in series. We have had problems in which the security has turned off the router, issues like that, contextual problems. There are issues with them running upgrades on their IT infrastructure, so you can't depend on their backhaul. So again, 100% network uptime is a myth, and your solutions can't depend, products can't depend on internet in general, right? The third is, again, with 5G coming in, with all the Reliance Jio plan, the first thing people say is data is cheap, right? But I'll again come to the exact calculations for some metrics. But once you start streaming hundreds of GBs of data every day, suddenly you realize that whatever you're paying as a SaaS fee or OpEx, whatever you're paying, you really did not budget for the internet cost of streaming. And I'll come to why streaming is there. And the last point, I think, manufacturing is push back for OpEx pricing model. This is a very interesting point. You got to realize how manufacturing buys, okay? How any kind of manufacturing looks at an asset, and they're like, I'm going to buy this for, suppose, 1 CR, and I'm going to depreciate it in my books for the next 10 years. I'm going to make this much money. Now, when you go and try to sell SaaS systems, I think anyone who has tried to sell SaaS to manufacturing, they'll always ask you what's the one-time fee and what's the AMC. And typically they're used to this one-time fee and AMC kind of model. And AMC is typically 10% of your contract. So that's not how SaaS scales. That's not how SaaS is priced or any of that. So manufacturing has a major pushback to any of these SaaS or continuously priced. Pay a lakh every year or every month, these kind of models. So I think this is an interesting point where manufacturing really likes edge systems, where you say that, you pay me this one-time cost for setting up my application in the edge, and a 10% AMC just to manage, because we as a company also don't incur much cost in a cloud servers because everything's happening on the edge, right? So yeah, so these are the 4 manufacturing related what we have found out over, this is not from any Gartner research, this is actually from the field that we have found out, right? Now quickly come to what we do as a product, what we build. So divided into 4 layers, the green dotted line is kind of what, segregates the cloud part, which is on top. We do use cloud, and, and the edge part. So at the bottom, you have our high-frequency sensor engines. Basically, if you look at any AI-based machine learning application for industries, you really need granular data. You need high-frequency data. You cannot be polling data every 2 minutes and expect a model to predict failures, right? We do asset-specific digital twins. So we do not have one model that works for everything from all kind of factories. We have these models for specifically stamping, welding, CNC, and packaging. These are the particular machine or asset classes in manufacturing that we kind of focus in. On top of which we have an analytics engine. This is more basic analytics, as someone was talking about productivity every day. That's simple mathematics. That's not any AI. And you have your Jarvis AI engine. These AI engines are for predicting quality defects, predicting machine failure, these kind, right? Post this, where we have our Insight Delivery engine. So this is the engine that is kind of hosted on our cloud servers because you need connectivity to send somebody a push notification. You can't do that from the edge. So these Insight Delivery engines deliver multiple kinds of insights, starting from workflows, efficiency insights, across kind of availability, performance, and quality. So as you see this whole product, essentially what it tries to do is improve your APQ, that is availability, performance, and quality in industries, and that's what you kind of focus on, right? Yeah, so I'm going to right now take a very particular use case that's one of our most deployed products as well as most appreciated. That's predictive maintenance. The goal of predictive maintenance is to kind of predict an equipment failure before that happens. Typically, how industries maintain equipments is they wait for a machine to fail, and after it's failed, they have spares, so they replace it. There's a whole, or if they don't have spares, it comes in a few days. So there's this whole downtime period because of an unexpected failure. Or the other case in which they do is, kind of do it before schedule. They do it every 6 months, in which the asset is not completely utilized, right? So again, the goal of predictive maintenance is to kind of predict equipment failure. So what you need for predicting failure is health data, and one of the key health parameters for any machine in any industry is vibration. That tells you for any mechanical equipment, that is. So what we essentially do is capture high frequency granular data. We have deep learning based models that kind of do anomaly detection. And then finally, if there's an anomaly, we kind of do a state prediction to see what kind of a state that anomaly lies in. So that's what we do. I'm going to tell you right now why edge computing is, this solution fails without edge computing, and we have deployed this on the cloud and we have failed. So, and then we obviously have the edge solution now. So if you look at the data points, we have like typically a 3-axis vibration sensor, that's X, Y, Z, capturing a data packet every second. That is almost 20 KB of data in a second. I'm talking about simple sampling rates of 1K, I'm not even talking really high frequency. 1K is still low frequency. That's almost 1.6 GB per day that a single machine kind of generates. And that's just one data stream. So we have vibration, you have other data streams like power consumption, you have temperature and so on, And then, you scale it across 30 machines, you have 50 GB per data per day, This is the amount of data you have to keep streaming to your model that's running on cloud to kind of generate insights, right? What we do right now is we kind of acquire, process, and generate the insight at the edge. We have deployed this whole solution at the edge. What we send to the cloud is just the insight, right? And the advantages out of this is continuous uptime. That is, again, the machines don't wait for internet to come back. If they're producing, they'll keep on producing. And if you can't show that insight in an HMI, the system is not working. It can be anything. So this kind of system is continuously working there. The other bit is latency, which I'll come in the next slide. These machines, any manufacturing produces anywhere between 30 to 1,000 parts a minute, right? The latencies associated with cloud computing can't meet any of this. And finally, this is, it saves a lot of cost, and this is actually cost for both the customer as well as us. We have benchmarked our server cost when we were internet only versus edge. There's almost a 1/10 difference in, the cost. So, you have to pass these costs down to your customers, and that's when, everyone talks about IoT scaling up from POC to full scaling plants. This is what happens when you scale from one POC to 30 machines. Suddenly, this is a cost, that's how it multiplies when you have just IoT kind of solution. So yeah, so this is I think, some validation of how edge computing is really required in this kind of a use case. The second use case, another interesting bit, this is actual numbers from our deployment at ITC. So typically the machine there works at about 300 parts per minute. So, and what we are doing there is kind of predicting the quality of this image is not an ITC image, I couldn't use there because of our NDAs. But typically they produce between 300 parts. That's 200 milliseconds is all you have between to say if that part is good or not. After that, the machine is supposed to either reject it or is supposed to say it's good, right? And these are all the steps that you typically need to do for any of these vision-based applications. There's acquire, filter, augment, process. You got to run your inferencing and kind of store the results. All of this to get GNG is good, not good. It's a manufacturing term again. So this is the case in which latency is, you just can't do this in the cloud. I have some numbers in the bottom, whatever internet, connection you take, you can't just do this with the latencies that come with cloud computing, right? So this is another case in which we have deployed our solutions with edge computing, kind of reinforce the fact that edge is the way forward. And finally, I still have 7 minutes left, but I'll have some time for Q&A. But a lot of talk about cloud, being dead in the future, or is cloud. We don't see that happening. Right now, architecture is very hybrid, to be honest. This is how it's kind of divided. And this is what even Prasad was speaking about, that things like training workloads, these edge systems, however powerful, however performance per watt they're trying to improve, they're not really out there for your training workloads, right? Then you talk about device management, something that Bipin spoke about at Gaia, right? So you have distributed edge devices across, suppose, 10 factories. You can't have 10 engineers at 10 factories trying to manage these. So you need this management layer, this device management layer that has to be obviously deployed in the cloud for connectivity. Again, a device management layer does not need to be real time, right? That can be done once a day or once an hour. So essentially this, if you see the bifurcation, is mostly anything that needs to happen in real time in industries, you have to have edge-based solutions. That's been a key learning, and that's where our product is. Anything that needs to be managed requires notifications and connectivity is what we have on the cloud. This is a layer which people do not talk about much, but a lot of development and products need to come out in this. Is how do you seamlessly sync your edge devices and your cloud? So you obviously have your Azure IoTs, and some of Google GCP has some edge softwares. But whatever we have tested is this particular stack. This is not about optimizing DNNs or CNNs on the edge. It's more about a lot of infrastructure code that needs to exist between your cloud and edge devices to make everything work seamlessly, right? And this is where we also actually spend quite a bit of our effort trying to build these interfaces between the edge and the cloud devices, apart from all the high-tech AI stuff also, right? Yeah, so this is more or less what I had in terms of how we leverage edge computing in industrial applications. Whatever I spoke about, these are not theoretical. We have deployed them in factories and are in production, so far to say. I have 5 minutes, so I would love to take a few questions.
Yeah, could you have mics, please? If anybody has questions, please raise your hand.
Someone there.
It's interesting that you've put in retraining as part of the edge.
Yep.
Any particular, was that for normal data or vision data?
So it's for both kinds. So what I meant by retraining is you probably have whatever your net is, the bulk of the training has to happen on the cloud, or whatever, depending on the architecture. And of course, that typically this is what we do. We deploy it, and no model is perfect. It's going to have whatever 94, 95% accuracy. And then, the contextual data of the industry needs to flow back. You're going to have false positives. So we have a system in which, the industry kind of defines these false positives, what is good, what is bad. And the second layer of retraining is something that can happen on these devices. So we have had some experience on some NVIDIA-based Jetson and 3X2, these kind of devices. They're not that bad at retraining, but the first training, which is, and also there's a lot of IP in some bit of a model architecture, which I can't discuss, in which we have a way in which certain bits of the layers are updated in a retraining process, which leverages the GPU at the edge, which can be achieved in a few minutes. That's, I'm talking about 5 to 10 minutes at the edge. So that's what I meant. Any other questions?
Okay, thank you. Thank you very much for presentation. Can I have Rahul Arya please come and hand over the memento?